Welcome, my friends. Recall that a rational function is just the ratio of two polynomials. For example, f of x is equal to x squared minus x plus 5 divided by x plus 1 is a rational function. As rational functions are fractions, the denominator cannot equal 0, but when the denominator does equal 0, the graph will do one of two special things. If the point at which the function equals 0 cannot be cancelled by factoring, you have what is called a vertical asymptote at that point. Here is the graph of x minus 1 divided by x plus 1. The denominator cannot equal negative 1, and there is no way to cancel the factor of x plus 1 in the denominator, meaning x equals negative 1 will be a vertical asymptote. The graph will approach but never reach the vertical asymptote, which in this picture is at x is equal to negative 1. Typically, we denote asymptotes with dotted lines on the graph of a function. The reason the graph acts this way, approaching either negative or positive infinity as it approaches the asymptote is, when you get really close to x equals negative 1, the denominator of x plus 1 gets really small. What happens when you divide by something really small? Well, you get a huge number, approaching either positive infinity or negative infinity if a negative was somehow wrapped up into the problem. The slightly less common case is if the point at which the function equals 0 can be cancelled out by factoring, in which case you have a hole in the graph. Consider the rational function f of x is equal to 3x minus 12 divided by x squared minus 5x plus 4. This function can be factored as 3 times x minus 4 divided by x minus 4 times x minus 1. The factor of x minus 4 cancels, and we just have 3 divided by x minus 1. But the thing you can't forget is that you can never cancel out a domain problem. X could not equal 4 before we canceled out x minus 4, so after we simplify, we still have the restriction of x not equaling 4. That means that the graph has a hole, sometimes called a removable discontinuity at x equals 4. To find out where the hole is, plug in x equals 4 into the simplified expression. We get 3 divided by 4 minus 1, which is 3 over 3, or just simply 1. So the point 4, 1 will be a hole in the graph. Here is a picture of the graph. We have a vertical asymptote at x equals 1, as that is a value that makes the denominator 0 that can't be cancelled by factoring. You can also see the hole at 4, 1, since x equals 4 would make the denominator 0 in the original function, but was able to be cancelled, which is why we have a hole. Now you might remember the idea of multiplicity from graphing polynomials. Here is a brief refresher. The number of times a given factor appears in the factored form of a function is called the multiplicity of the factor. Consider this factored rational function. F of x is equal to x minus 2 squared times x plus 4 times x plus 1 divided by x plus 2 squared times x plus 4 times x minus 4. For the factors in the numerator, we have x minus 2 with a multiplicity of 2, which is an even number, so we label this as an even multiplicity. We have x plus 4, which occurs once and therefore is an odd multiplicity, and we have x plus 1, which also has a multiplicity of 1 and is therefore odd. On the denominator, we have x plus 2, which occurs twice, so the multiplicity is 2, which is even. The other two factors each have a multiplicity of 1 and are therefore odd multiplicities. All we really care about with regards to multiplicity is if it is even or odd and where it occurs, either in the numerator or denominator. The graph will have a hole for each factor that completely cancels, as we have already discussed. The factor of x plus 4 cancels on the numerator and denominator. As we already discussed, if you can cancel a factor, that means there will be a hole, and this will be the case regardless of the multiplicity. So this graph will have a hole at x is equal to negative 4, the point that would make the factor of x plus 4 equal 0. Once you've taken care of the holes, each remaining factor on the numerator will indicate a 0. These zeros can be real or imaginary, but in this case, they are all real. If the multiplicity of the factor is odd, the graph will cross the x-axis at that 0. if the multiplicity of the factor is even, the graph will bounce off of the x-axis at the 0. There will be a 0 at x is equal to 2 for the factor of x minus 2, as x equals 2 makes this factor equal to 0. The graph will bounce off the x-axis at this point because the multiplicity is even. There will be another 0 at x equals negative 1, as that is where the factor is equal to 0. The graph will cross the x-axis at this point because the multiplicity is odd. As we discussed earlier, the graph has a vertical asymptote for each remaining factor on the denominator. If the multiplicity is odd, the graph will approach the asymptote at opposite infinities. If the multiplicity is even, the graph will approach the asymptote at the same infinity, either negative infinity on both sides or positive infinity on both sides. So we will have two vertical asymptotes in our function, one at x is equal to negative 2 for the factor of x plus 2 squared, and another one at x equals 4 for the factor of x minus 4. The difference between them is that the asymptote at x equals negative 2 has an even multiplicity, and the asymptote at x equals 4 has an odd multiplicity. For vertical asymptotes that have an even multiplicity, like x equals negative 2, you will approach the same infinity from both sides. So the graph will either approach positive infinity on both sides of the asymptote, or negative infinity on both sides. For odd multiplicity vertical asymptotes, like x equals 4, you will approach a different infinity from either side. So that is, you approach positive infinity on one side and negative infinity on the other side. Here is a summary of everything from the previous slide about this graph. The graph will have a hole at x is equal to negative 4, as the factor x plus 4 cancels. It will have zeros at x equals negative 1, which will be a cross of the x-axis due to the odd multiplicity, and there will be another 0 at x equals 2, which will be a bounce due to the even multiplicity. There will be vertical asymptotes at x equals negative 2, which the graph will approach at the same infinity due to the even multiplicity, and another vertical asymptote at x equals 4, which the graph will approach at opposite infinities due to the odd multiplicity. Here's the graph of this rational function. Let's talk about how each factor determines the behavior of the graph. First, notice that we have a hole at x equals negative 4, since that factor canceled. Let's talk about the two zeros. You can see that the graph crosses the x-axis at the 0 of x equals negative 1. This is because x equals negative 1 had an odd multiplicity. Also notice that the graph bounces but does not cross the x-axis at the point of x equals 2. This is because x equals 2 had an even multiplicity, so the graph will not cross the x-axis at that point. Then we can look at our two vertical asymptotes. The first vertical asymptote is at x is equal to negative 2, which we indicate with a dotted line on the graph. Notice that on either side of the asymptote, the graph approaches positive infinity. We approach the same infinity on either side of the asymptote, positive infinity on both sides, because the factor of x plus 2 has an even multiplicity. The other asymptote at x is equal to 4 approaches negative infinity from the left and positive infinity from the right. We approach opposite infinities because the multiplicity of x equals 4 is odd. So in summary, if a factor cancels, that will indicate a hole in the graph. Of the remaining factors, wherever the numerator is equal to 0 indicates an x-intercept. Factors on the numerator with an odd multiplicity indicate where the graph crosses the x-axis, and factors on the numerator with an even multiplicity indicate where the graph bounces off of the x-axis. Any remaining factors that didn't cancel in the denominator will indicate vertical asymptotes. Factors on the denominator with an odd multiplicity indicate vertical asymptotes where the graph approaches opposite infinities, and factors on the denominator with an even multiplicity indicate where the graph approaches the same infinity. Now you may recall that when we had polynomials, there were basically 4 cases of what we called end behavior, meaning 4 different options for what the function could do as we approached negative and positive infinity. The end behavior of a polynomial is determined by the leading term, meaning the term with the highest degree. For even degree polynomials with a positive leading coefficient, we approach positive infinity in both directions. For even degree polynomials with a negative leading coefficient, we approach negative infinity in both directions. For odd degree polynomials with a positive leading coefficient, we approach positive infinity as x increases and approach negative infinity as x decreases. For odd degree polynomials with a negative leading coefficient, we approach negative infinity as x increases and positive infinity as x decreases. For rational functions, we have these four options as well as a few additional options. Case 1 is when the degree of the polynomial on the numerator is at least 2 degrees higher than the degree of the denominator. For example, this rational function has a degree of 5 on the numerator and a degree of 2 on the denominator. So the degree of the numerator is 3 more than the degree on the denominator, so we fit case 1. This polynomial has a degree of 3 on the numerator and a degree of 1 on the denominator, so this also fits case 1, as the degree of the numerator of 3 is at least 2 degrees higher than the denominator. This polynomial has a degree of 2 on the numerator and a degree of 3 on the denominator, and therefore does not fit case 1. If you have case 1, then the end behavior will match the polynomial found by simplifying the ratio of leading terms. For example, consider x to the 4th power minus 1 divided by x squared minus 2. Only considering the leading terms, we have x to the 4th power divided by x squared, which simplifies to x squared. The end behavior of x squared is that of a parabola approaching positive infinity as x increases or decreases. Here is the graph of this function. You can see that as we approach either negative or positive infinity, the graph increases towards positive infinity, in sort of the parabola type shape. Yes, it does something else a little bit weird in the middle, but the end behavior is the same direction as a parabola would have. Case 2 is when the degree of the denominator is higher than the degree of the numerator. In that case, the denominator will get much larger in absolute terms than the numerator for really positive or really negative values for x. This leads to the function approaching 0 as x approaches positive or negative infinity. Graphically, this creates a horizontal asymptote at y equals 0, which is the x-axis. For example, consider the rational function f of x is equal to 5x plus 1 divided by x squared minus x minus 6. The degree of the numerator is 1, and the degree of the denominator is 2. For this reason, we have case 2, which indicates that the end behavior will be a horizontal asymptote at y equals 0, which is the x-axis. Graphically, here is what the function looks like. We can see that as we approach positive infinity, the graph approaches y equals 0, the x-axis, and as we approach negative infinity, the graph also approaches the x-axis. Case 3 is when the degree of the denominator is the same as the degree of the numerator. In this situation, you will have a horizontal asymptote at y equals the ratio of the leading terms. For example, consider the rational function f of x is equal to 4x squared plus 2x plus 2 divided by x squared minus 1. The degree of both the numerator and denominator is 2, which tells us that we match case number 3. The ratio of the leading terms is 4x squared divided by x squared, which is just 4. Therefore, there will be a horizontal asymptote at y is equal to 4. Here is the graph of this function. Notice that as we approach positive or negative infinity, the graph gets closer and closer to y equals 4. Also notice that the graph actually does cross the horizontal asymptote at around x is equal to negative 3, and then start to come back up to it. This is a difference between vertical and horizontal asymptotes. You can never cross a vertical asymptote, but horizontal asymptotes will sometimes be crossed. You can find where a horizontal asymptote is crossed by setting the rational function equal to the horizontal asymptote and solving for x, which we will do in a separate video on graphing rational functions. The final case is when the degree of the numerator is 1 higher than the degree of the denominator. This case could have technically been lumped in with the end behavior of polynomials case, but it is usually thought of separately. If the degree of the numerator is 1 higher than the degree of the denominator, then there is what is called an oblique asymptote, or sometimes called a slant asymptote. This is when the function approaches a straight line with the equation y equals mx plus b, as x approaches infinity or negative infinity. To find the equation of the line that the graph will approach, you have to do polynomial long division. Consider f of x is equal to x squared plus 10x plus 8 divided by negative 2x minus 4. The degree of the numerator is 2 and the degree of the denominator is 1. As the degree of the numerator is 1 higher than the degree of the denominator, this rational function will have an oblique asymptote. If you do polynomial long division, you will have negative 2x minus 4 on the side and x squared plus 10x plus 8 on the inside. X squared divided by negative 2x is negative 1/2 x, which goes on top. Multiplying, we have negative 2x times negative 1/2 x, which is x squared, and negative 4 times negative 1/2 x, which is 2x. Subtracting, we have x squared minus x squared, which is 0, and 10x minus 2x, which is 8x. Then we bring down the 8. 8x divided by negative 2x is negative 4. Once you have all the numbers on top, you can stop the long division. You don't have to complete it. This function has an oblique asymptote at y equals negative 1/2 x minus 4. Here's the graph of this function. You can see that there is an oblique asymptote at y is equal to negative 1/2 x minus 4, which is the dotted line. The graph approaches the asymptote and gets closer and closer to it as we approach negative or positive infinity. Let's summarize everything we have talked about so far. Factors that can be cancelled create holes in the graph. In this example, the x minus 2 factor would cancel, resulting in a hole at x is equal to 2. Any remaining factors in the numerator create zeros, which will cross the x-axis if the multiplicity is odd, and bounce off the x-axis if the multiplicity is even. Note that some zeros could be imaginary, meaning they won't be real crosses of the x-axis. In this example, x is equal to negative 4 has an even multiplicity, so the graph will bounce off the x-axis at that point, and x is equal to 3 has an odd multiplicity, so the graph will cross the x-axis at that point. Any remaining factors in the denominator create vertical asymptotes, which the graph will approach at opposite infinities if the multiplicity is odd, and approach at the same infinity if the multiplicity is even. In this example, there will be a vertical asymptote at x is equal to negative 6, which the graph will approach at the same infinity as the multiplicity is even, and there will be another vertical asymptote at x is equal to negative 2, where the graph will approach opposite infinities as the multiplicity is odd. If the degree of the numerator is at least 2 degrees higher than the degree of the denominator, the graph will match that of the polynomial found by simplifying the ratio of leading terms. In this example, the ratio of the leading terms would be a positive cubic, so the graph will have an end behavior that matches a positive cubic function. If the degree of the numerator is less than the degree of the denominator, there will be a horizontal asymptote at y equals 0. In this example, the degree of the denominator is 1 higher than the degree of the numerator, meaning there will be a horizontal asymptote at y equals 0. If the degree of the numerator and denominator are the same, the graph will have a horizontal asymptote at y equals the ratio of the leading terms. In this example, the ratio of the leading terms is 4 over 2, which is 2, meaning there will be a horizontal asymptote at y equals 2. If the degree of the numerator is exactly 1 higher than the degree of the denominator, the graph will have an oblique asymptote, which can be found through polynomial long division. This function will have an oblique asymptote, which we could find by doing polynomial long division. Let's look at some examples putting everything together. Consider the function f of x is equal to negative x plus 2 times x minus 5 squared times x minus 1 divided by x minus 2. This function is already factored, which is nice. Sometimes it won't be. Let's determine the following things about this function. What the end behavior is, being either a horizontal asymptote, an oblique asymptote, or matching the end behavior of a polynomial. Find the holes and or vertical asymptotes as well as their multiplicities, and find the x-intercepts and their multiplicities. As far as end behavior, we notice that the degree of the numerator is 4, since we have 4 factors of x, and the degree of the denominator is 1. This is what I called case 1 earlier, when the degree of the numerator is at least 2 degrees higher than the degree of the denominator. Also notice that we have a negative sign out front, which is important. Subtracting the degrees, we will match the end behavior of a negative cubic, which will look something like this. Next, let's determine the holes and or vertical asymptotes. We don't have any holes because none of our factors cancel. Instead, we have a vertical asymptote at x is equal to 2, which has an odd multiplicity, meaning the graph will approach this asymptote at opposite infinities. As far as x-intercepts, we have x is equal to negative 2, x is equal to 5, and x is equal to 1. X is equal to negative 2 and x is equal to 1 have odd multiplicities, meaning the graph will cross the x-axis at these points, and x is equal to 5 has an even multiplicity, meaning the graph will bounce at that point. Here is the graph of the function. Notice that the end behavior matches what we stated. It approaches negative infinity as x increases and positive infinity as x decreases, just like a negative cubic. The x-intercepts can be seen at negative 2, 1, and 5. The intercepts at negative 2 and 1 cross the x-axis as we had an odd multiplicity, and the intercept at x equals 5 bounced as we had an even multiplicity. The vertical asymptote can be seen at x is equal to 2, and the graph approaches opposite infinities at this asymptote, so the multiplicity is odd. Let's try another one. Say we have f of x is equal to x squared plus x minus 6 divided by x plus 4. Let's first talk about the end behavior. This will have an oblique asymptote because the degree of the numerator is 1 higher than the denominator. Setting up long division to find the oblique asymptote, x squared divided by x is x. X times x is x squared, and 4 times x is 4x. Subtracting, we get 0 and negative 3x. We can bring down the negative 6, but we don't really need to. All we need is the next number on top, which will be negative 3, because negative 3x divided by x is negative 3. We don't need to finish the long division. We know that the oblique asymptote will be at y is equal to x minus 3. The denominator indicates that we will have either a vertical asymptote or a hole at x equals negative 4. To know for sure, we need to factor the numerator. We have x plus 3 times x minus 2, as 3 times negative 2 is negative 6, and 3 plus negative 2 is 1. Since the factor of x plus 4 doesn't cancel with anything, we know that x is equal to negative 4 is a vertical asymptote, which has an odd multiplicity, meaning the graph will approach opposite infinities. The numerator tells us that we have zeros at negative 3 and 2, which both have an odd multiplicity, meaning the graph will cross the x-axis at these points. Here is the graph of this function. You can see the oblique asymptote, which has the equation y is equal to x minus 3. You can also see the vertical asymptote at x is equal to negative 4, which the graph approaches at opposite infinities on either side. You can also see the two zeros of x equals negative 3 and x equals 2, which the graph crosses the x-axis at, since the multiplicities are odd. How about f of x is equal to 3x squared plus 12x plus 12 divided by x squared minus 1? Since the degree of the numerator is the same as the degree of the denominator, we have a horizontal asymptote at the ratio of the leading coefficients, which is 3 divided by 1, or just 3. The equation of the horizontal asymptote is y equals 3. We can factor the numerator by pulling out a 3 to get 3 times x squared plus 4x plus 4, and factor the denominator by a difference of squares to get x plus 1 times x minus 1. The numerator can be further factored to 3 times x plus 2 squared. This tells us that there is a vertical asymptote at both x equals 1 and x equals negative 1, which both have a multiplicity of 1, meaning they will be approached at opposite infinities. And there is a 0 at x is equal to negative 2, which has a multiplicity of 2, meaning the graph will bounce and not cross the x-axis at that point. Here's what the graph of the function looks like. We have a vertical asymptote at x is equal to 1 and x is equal to negative 1, which are approached at opposite infinities, and then we have a horizontal asymptote, which can be seen at y equals 3, which is crossed here in the middle of the graph, but the graph does approach y equals 3 as we approach positive or negative infinity. We can see the 0 at x equals negative 2, which the graph bounces off of due to the even multiplicity. Okay, one last problem. Say we have f of x is equal to negative 3x plus 15 divided by x squared minus 7x plus 10. This graph will have a horizontal asymptote at y is equal to 0, which is the x-axis, since the degree of the denominator is larger than the degree of the numerator. the numerator can be factored as negative 3 times x minus 5, and the denominator can be factored as x minus 5 times x minus 2. The x minus 5 factors cancel, indicating that there is a whole at x is equal to 5. We also have a vertical asymptote at x is equal to 2, with an odd multiplicity. There are no zeros since the only factor on the numerator canceled. Here's the graph of this function. We can see the whole at x equals 5 and the vertical asymptote at x is equal to 2, which is approached at opposite infinities on either side due to the odd multiplicity. The graph also approaches the horizontal asymptote of y equals 0 as x approaches either positive or negative infinity. Alright my friends, that wraps up our video on the asymptotes of rational functions. In the next video, I will show you how to take all of this information and graph the function yourself.